My name is Jasmine, and I'll be talking about 11.2 patterns and symmetries. Okay, so first we're going to talk about a symmetry of a plane figure. The symmetry of a plane figure is any rigid motion of the plane that moves all the points of the figure back to the points of the figure. Okay, so the next thing we're going to talk about is reflection symmetry. Reflection symmetry is a figure that has reflection symmetry. F, a reflection across some line, is the symmetry of the figure. The line of reflection is called line of symmetry or mirror line of the figure. Okay, so now we're going to do some examples of identifying lines of symmetry. We're going to do 4 of them, so here are our first 2. So for this smiley face, we need to figure out what way can we split this smiley face to where it's exactly the same on the other side. So if we split it this way, that would not work because the 2 sides are not the same. It may be the same area, but it is not the exact same within the other shapes that are inside. So that would not work. We can't split it diagonal. The only way we can split this is if we go straight down the middle. And that gives the exact same thing on both sides. So that is one way we can split this figure. So with this figure right here, I can't split it this way, can't split it this way, can't split it this way, cannot even split it this way, because they're not the exact same on each side since the arrows are going opposite ways. So this is 0. We cannot make that a line of symmetry anywhere. Okay, so for our next 2 examples, we have a theta symbol and a plus sign symbol. So for this symbol right here, we know that we can't go diagonal because that would not be even. But you can go down because that would make it equivalent on both sides. But even when you can go down, you can also go across because that will also make it equivalent on both sides. So this one has 2 lines of symmetry. So now moving on to the plus sign. This one has a lot of them. So you can go down right here, across right here, because it's going to be equivalent on both sides regardless. You can also go diagonal and another diagonal, because no matter which way you go, it will be equivalent on both sides. So this one right here will have 4 lines of symmetry. Okay, so moving on to rotation symmetry. A figure has rotation symmetry or turn symmetry if the figure is superimposed on itself when it is rotated through a certain angle between 0 degrees and 360 degrees. The center of the turn is called center of symmetry. Figures which turn onto themselves after any turn about their center have circular symmetry. Okay, so we're finding angles of rotation symmetry, and we are determining the measures of the angles of rotation symmetry of these figures. So we're going to do 4 of them, and here's the first 2. So for A, we have a regular hexagon. We're trying to see how many times could we turn this hexagon for it to keep looking like itself. So if we start right here, and you turn it to this point, that's 1. And then you come around and turn it to this point, that's 2, 3, 4, 5, and then you can turn it one more time to get it back to itself, which is 6. So now, since we have that 6, we can go ahead and answer the problem. So we're going to take 360 and we're going to divide it by that 6 that we got. So now when we divide that by 6, we will get 60 degrees. And now we have to find the multiples of 60 degrees to get our whole answer. So 60 times 2 is 120. 60 times 3 is 180. 16 times 4 is 240. 60 times 5 is 300. And then, of course, we have 60 times 6, which is 360, but we cannot include 360 into our answer since that it has to be between 0 degrees and 360 degrees. It cannot be 360, it has to be between. So we cannot include that in the answer. Therefore, it would just be 60, 120, 180, 240, 300 angles. So here, we'll just have a regular little oval. And we're trying to see how many times we can turn that to get it back to itself. So you turn it here. It's 180 degrees. You can only turn it 180 degrees to get it back to itself, because you turn that once, it'll still be the same shape. So 180 degrees will be our only answer for that example right there. Okay, so now moving on to the other two examples. We have a 9-sided polygon and we have a circular figure. So with this 9-sided polygon, we already know that it has 9 sides to rotate it, just like we did with the hexagon. So we can go ahead and divide 360 by 9, which gives us 40 degrees. So now we need to find the multiples of 40 that is between 0 degrees and 360. That will give us the solution. So 40 times 2 will give us 80 degrees. 40 times 3 will give us 120. 40 times 4 will give us 160. 40 times 5 will give us 200. Times 6 will give us 240. Times 7 will give us 280. Times 8 will give us 320. So all of these right here will be a solution to this. So now we have a circular figure. And we already mentioned before, if you turn a figure and it just turns right back into itself, that is called circular symmetry. So this right here will just simply be circular symmetry. Okay, so now moving on to point symmetry. A figure has point symmetry if it has 180 degree rotation symmetry about some point O. So if we take this playing card of spades and we get this corner right here and rotate it 180 degrees, to this will correspond to this point, given the fact that if you flip this card 180 degrees, it will be the exact same card. So that will make it have point symmetry about point O, which will be right here. Even if we got this point to this point, it would still have point symmetry about point O and be the exact same card flipped over. Therefore, this figure has point symmetry. Okay, so now moving on, we are identifying point symmetry. What letters in uppercase block form can be drawn to have point symmetry? And this is in our alphabet. So if you think about it, the first one we have is uppercase H. Because if we go about this point right here, you can flip that 180 degrees and it'll still be the same uppercase H. We have uppercase I, flip it right there. Uppercase N, about this point right here. Uppercase O, this point right here. Uppercase S, this point right here. Uppercase X, this point right here. And last but not least, uppercase Z, this point right here. So all of these uppercase alphabetical letters can be flipped 180 degrees and still be the exact same letter as it is rotated 180 degrees. It has point symmetry. Okay, so now moving on to periodic patterns. A periodic pattern is a figure with translation symmetry. That is, there at least one translation that moves the pattern so that it is superimposed on itself. Two types of periodic patterns in the plane are border patterns and wallpaper patterns. Okay, so now we're talking about border pattern classification. To find the classification symbol of any border, follow the steps. So we have the first symbol. The first symbol will be M if there's a vertical line of symmetry, and it'll be a 1 otherwise. For the second symbol, it'll be an M if there's a horizontal line of symmetry. G if there is a glide reflection symmetry, but no horizontal line of symmetry. 2 if there is half turn symmetry, but no horizontal line of symmetry or glide reflection symmetry. And it is 1 if it is otherwise. Okay, so now we're classifying border patterns. So classify the symmetry type of the following border patterns by assigning the appropriate 2-symbol notation. So here we have a horizontal line and a vertical line. So that would give us M, like the symbols we just talked about before. Here we do not have any lines of symmetry going vertical or horizontal, but we do have a glide symmetry. So that would give us 1G. And here we do not have no lines of symmetry going horizontal or vertical, but we do have the half turn symmetry. So that would give us 1, 2. And all of those symbols came from the previous slide we just did with learning how to categorize the symbols. Okay, so moving on to wallpaper patterns. We have a wallpaper pattern has translation symmetry in at least 2 directions. So starting with this wallpaper, we figure that it is 60-degree and 120-degree rotation symmetry, and at these Z shapes, you have 180-degree rotation symmetry. And then on this wallpaper, you have 90-degree rotation symmetry. And you also know that 60 degrees, 120 degrees, and 180 degrees have rotation symmetry there. So given that both of these have more than one rotation symmetry, that these are, in fact, wallpaper patterns.